Hey, before we start today, I want to warn you really quick about next week, which is the last week that should be messed up for me. I'll tell you guys probably today and Thursday, just so everybody catches it. So next week, which would be, oh, don't want to zoom in. I don't know what happened there. Hang on. All right, so next week, which would be the March, what is it, 6th, I guess, the week of March 6th. There's not going to be any office hours. I'll be out of town for a conference, so I'll still be available by email and things like that, but I won't be able to have in-person office hours. And we'll still have class, though. I'll have replacements coming in. Tuesday will be Professor Gloy, and Thursday will be Larson again. So based on how they usually do things, Gloy will probably cover the same topic, but likely with different format, and Larson will most likely try to cover exactly the same thing that I was planning to cover. I will post recorded videos just for continuity, so if you prefer to keep up with it that way, that's fine as well. That should be the last time that things get messed up for me, although on top of everything else I've had, I did also get called for jury duty, but that should only affect my spring break and not actual class time, so we'll see how that goes. But I won't know until after spring break whether that's going to affect anything. All right, but on to today's stuff. So first I'll give you a rundown of how we did on the first exam, which ended last week, except for the very few people that have makeups this week. So the average this year was a smidge higher than last, so we are trending upward, which is good to see. Slow progress, but better than no progress. So we had this year an average of 13.9 out of 20, which is just under 70%. And there were 4 students that got perfect scores. So that was the highest score that anyone got on this was 20 out of 20. So this is the distribution of scores. You can see that 14 and 15 out of 20 were the 2 most popular scores, but there was a distribution across a wide range. So obviously we'll have 3 more exams. So this is only a small piece of the puzzle in terms of your grade. If you're happy with how you did, that's great. Keep it up, but also recognize that the average for the second exam does tend to be a little bit lower, so you can't get complacent. And similarly, if you're not happy with your exam, you have to very quickly identify sort of some changes in habits that you're going to need to do better in the future. And I'm happy to discuss any of those with you as we go forward. All right, so take a look at that if you're interested in how everybody did, but there we go. Okay, so let's move into today's material. So we're continuing in chapter 5, which is all about moles as kind of the central concept that brings this whole chapter together. And so what we're going to talk about today, last time we discussed how we can use the chemical formula to determine the mass percents of the elements. So we're talking about this relationship between chemical formula and mass percent, a topic that we had covered a long time ago at the very beginning. And today we're going to learn how to go in the opposite direction, which is taking the mass percents of elements in a compound and determining the chemical formula. Now the reality though is we'll see that this approach doesn't directly give us the molecular formula, it gives us what's called the empirical formula. So let's discuss the difference between those two first. So as we know, we've already talked about this in several contexts, the molecular formula tells you the total number of each atom in a molecule of a compound. So if you have one molecule of that compound, the formula tells you how many of each atom would be there. So CO2, H2O, etc. Those sort of, for covalent compounds in particular, that's how we would think about it. Now the related concept that we're going to talk about today is the empirical formula, which is the lowest whole number ratio of atoms in that compound. And the reason we have to talk about this is not because it's particularly useful on its own, but because if we're using mass percents as a way of determining chemical formulas, what we would initially get at least is just the empirical formula. So we can't use the mass percents to get the full molecular formula, it only would give us the empirical formula. Now, one thing to keep in mind when we do this, we're going to mostly talk about this in the context of covalent compounds, but if you're talking about an ionic compound, remember that for ionic compounds, we always write it in terms of the lowest whole number ratio of the ions. That's conventionally how we do it. So in this case, in almost every case anyway, the empirical formula would be equivalent to the ionic formula. There could be rare exceptions to that if you have polyatomic ions that don't reduce down to their lowest whole number, but I don't think any of the ones that we dealt with would have that problem. So you probably won't see it. So in our case, for our purposes, we could say that for an empirical formula, for an ionic compound, if you have the ionic formula, that is the empirical formula. Those two are equal to each other. But for many covalent compounds, that's not the case. So here's some examples of the relationship between molecular formula and empirical formula. So if we had N2H4, this is called hydrazine. It's used as part of a rocket fuel mixture, as it turns out. So this is not the lowest whole number ratio of nitrogen and hydrogen in this compound. So one molecule of this compound would have 2 nitrogen atoms and 4 hydrogens. That's how we would write the molecular formula. But the empirical formula that we would get from that, we can divide everything by 2 to reduce the lowest whole number. So it would be written as NH2 for the empirical formula. And then, but if we have H2O, this one we can't reduce at all because we have already just a coefficient of, or subscript of 1 in oxygen. You can't reduce that to a smaller whole number. So this one we can't really reduce at all, and it just has the same empirical formula. So there are a lot of compounds where the molecular formula and the empirical formula are the same, but there's also many where that's not the case. So if we go to C6H6, if you remember that delocalized cyclic structure we talked about benzene at the end of chapter 4, that's the formula C6H6. And if we want to find the empirical formula of that, we have a common factor of 6 on both of those, so we can divide both by 6 and get to an empirical formula of CH. And then this compound here, B3N3H6, which is a sort of a boron nitrogen analog of benzene, as it turns out. We have a greatest common factor of 3, so if you divide all those by 3, you get BNH2. So if you're asking, to convert from the molecular formula to the empirical formula, then you just divide by the greatest common factor of all the subscripts. And so, there's going to be many compounds that have the empirical formula CH. It could be C2H2 or C3H3 or C4H4. So there's a lot of possible compounds that have the same empirical formula. But the reason we're introducing this is because, as we're going to learn here in just a little bit, if I give you the mass percent of the elements in a compound and you don't know the chemical formula of that compound, you can use that as part of your method to find it, but it will only give you the empirical formula, not the molecular formula. In other words, any compound that has the same empirical formula is going to have the same mass percentages. So you can't distinguish compounds that way if they have the same empirical formula. All right, so let's talk about the steps then of how we do this. If we give you the mass percents or the masses of elements in the compound, how do we determine the empirical formula? So the first thing we do is, now that we know how to do this, this is one of the first things we introduced in chapter 5, we convert the mass of each element into the number of moles. Okay, because remember that the empirical formula and the molecular formula, they tell you the mole ratios of each element in the compound. So we're going to convert the mass to moles first, and we use the atomic mass to do that, as we learned how to do last week. And then what we have to do, though, is usually when we do that, we're going to get a bunch of decimal numbers. We're not going to get whole numbers right away from this. So then your next step is going to be to convert to the lowest whole number ratio. And the way that we do this is we divide all of the molar amounts by the smallest one. So we're going to have number of moles for each element, and to get them into a ratio, we divide each molar quantity by the smallest one. Okay? And then the third step, we only will do it if necessary. Unfortunately, I don't think any of the problems I give you today have this step involved, but I'll still show you how it works. This last step is a sort of an if necessary step. So sometimes when you do steps 1 and step 2, you don't get still whole numbers for all the coefficients. At least one of them will be 1 because you're normalizing to the smallest one, but some of them might not be whole numbers anymore. So if necessary, what you're going to do is multiply every coefficient by a small number to remove fractions or decimals. And you have to do the same thing mathematically to every subscript in the formula, because you don't want to change the ratio. You can't change the ratio of the elements, but you can multiply by a small number if necessary to convert them all into whole numbers. So an example of this last step, if you have, So let's say you did steps 1 and 2. And when you do that, one of the elements is always going to have a subscript of 1 because you're normalizing to that. But let's say we got C1.5H after we did steps 1 and 2. Now we don't want to have an empirical formula or a molecular formula that has decimals or fractions in it. So at this point, though, you don't want to round. A lot of people make the mistake in these types of problems of just rounding up. Oh, C1.5, well, 1.5 rounds to 2, it's just going to be C2H. But you don't want to round unless it's like really, really, really close to the whole number, like C1.98 or C2.02 or something like that. If it's far away from a whole number like this, you want to find some factor that you can multiply these by to get rid of the decimal or the fraction. So if you have a 0.5 in there, you should always multiply by 2. And so the correct empirical formula, if you got C1.5H, would actually be written as C3H2. So you'd have to do the same thing to both of them to keep the ratio the same. So then also if we got N 1.33H, let's say we're doing this compound. This is probably a nonsensical example, but mathematically it helps us understand this. So if you get something 0.33, again, that's going to be far away from a whole number. You don't want to just round that down to 1, so we multiply that by 3. If you have a 0.33 or a 0.67 in there, multiply everything by 3, and that'll give you, in this case, 3 times this will be N4H3, okay? So that would be the correct empirical formula of that. So you want to write them in whole number ratios, but you don't want to change the ratio. So if you're going to multiply by a coefficient, you have to do it for both of them. So you'll see problems like that sometimes in homework questions and tests where you do these first 2 steps, but you're still not at all whole numbers. I think the examples we'll do today, we can avoid this 3rd step just by chance, but sometimes that will be necessary. So my number 1 warning for these types of problems as you go through and learn how to do them is don't do too much rounding. There's a lot of people that make mistakes on these because they will round a 1.5 to a 2 or even a 1.75. That would be something you're going to multiply by 4. So usually it's going to be, multiply by 2 if it's 0.5, multiply by 3 if it's 0.33 or 0.67, multiply by 4 if it's 0.75 or 0.25. Rarely would you have to do anything more complicated than that, but make sure you're not rounding too much. Only if it's really close to the whole number should you round it off. All right, so this is going to be best learned by doing some examples. So one way that we can set up problems like this is we can give you the actual masses of all the elements. So in absolute terms, we can say, okay, we have a sample of this compound, which is called vanadial chloride. It's interesting because it's a metal compound, but it's a liquid at room temperature, which is not very common. But anyway, if we analyze this, we find that it has 1.47 grams of vanadium, 0.462 grams of oxygen, and 3.07 grams of chlorine. What is the empirical formula? So in cases like this, we're directly giving you the masses of the elements, so all we're going to need to do is just convert those into moles and then find their lowest ratio. So we'll find this, we'll do the moles for each element in any order, but we'll start with the vanadium, which is the first one given. So we have 1.47 grams of that element in the compound, and then we're going to convert into moles. Remember that when we convert to moles, we use the atomic mass, which you have to get from the periodic table. All right, so V is all right, there's V right there, number 23, and the atomic mass is 50.94. Okay, so we're going to use that atomic mass to convert to moles. And remember that if you write out your units, it helps you decide whether you multiply or divide. So we want moles in the numerator, we want grams to cancel, and so we're going to put that atomic mass in the denominator because it's going to be 50.94 grams of vanadium in 1 mole. That's the definition of the atomic mass. Okay, so when we do that, we get 0.0288 moles. All right, and then we're going to do the same thing for the other 2 elements, oxygen and chlorine. So for oxygen, we have 0.462 grams. And we're going to do the same step. We're going to convert into moles by dividing by the atomic mass. And so atomic mass for oxygen, we'll probably remember this one very soon because we're using it a lot. It's 16. Rounded to 2 decimal places is fine. So 16.00 for oxygen. So that's the atomic mass we'll use there. And we get pretty much the same number. Again, because of rounding and things, you might not get identical numbers. We got 288 up here, 289 down there, but those are essentially identical for the purposes of problems like this. We're trying to find the ratio. And then finally do the same thing for chlorine. So we have 3.07 grams. And I'm not going to flip back to the periodic table yet again, but for chlorine we do the same thing. We divide by the atomic mass. And if you look that up on the periodic table, or can see the one that's over on the far left of the room, 35.45 grams per mole for chlorine. So again, that's just the number straight off the periodic table. We don't have to do anything else with that. All right, so when we divide by that, we get a different number this time, 0.0866. All right, if they're all the same, then it's easy, because then the formula is just one of each. But they're not all the same here, so the next thing to do is we're going to divide by the smallest one. So technically speaking, this would be, the empirical formula of this compound. V 0.0288, O 0.0289, Cl 0.0866. But as we said, we don't want to write any sort of chemical formula or empirical formula with all kinds of decimals in it. We want to convert to whole numbers. So the way that we do that is we divide them all by the smallest. The smallest is V, which is 0.0288. So we're going to divide all of them by that. And so that what you end up with is that just becomes V. That basically is 1. That might be like 1.0001. Again, it's close enough to 1. We'll just say VO. And then that comes out to 3. So VOCl3 would be the correct empirical formula for this compound. And also its molecular formula, as it turns out. This is more of a molecular compound, even though it has a metal in it. All right, so that's how we would do it. We have to find the moles of each and then just divide to get the smallest ratio. So any questions on that? In here, we didn't have to do that last step because we got whole numbers directly from the first two steps of finding the moles and then normalizing. If any of these are decimals, and if any of these are far away from whole numbers, then you'd have to do that last step to convert to whole numbers. But here it wasn't necessary. All right, let's do then one more. And the other way that we could set this up is in terms of mass percents. So that problem we gave you directly the amount of grams of each element in the compound, but here we're just giving you the percentage by mass, which we learned again early on in the course is the number of grams of each element per 100 grams of the compound. So what is the empirical formula for a binary compound consisting of boron and fluorine that is 15.94% boron by mass? So there's going to be a few things here that we need to do before we can start doing all the mole conversions, because we don't have the masses of each element. We just have the mass percent of boron. So what we're going to do in problems like this is, well, the first thing we can recognize is that we need the mass percent of the other element as well. So it's a binary compound. That and the fact that we're only telling you that there's two elements in it tells us that this is a compound with only two elements in it. And so what that means then is that the rest of our 100% mass percentages has to be the other element, fluorine. So to find the mass percent for the other element, we just do it by difference. 100% is the total mass percent of all of the elements. The other one is 15.94. That's given to us. So this is total. This is the amount of boron in the compound. The rest has to be fluorine by conservation of mass. Okay, so 84.06. All right, so now we have mass percents of both boron and fluorine, but we still have to figure out, well, how do we deal with mass percents? These aren't actual, gram amounts. How do we convert them into moles? Well, what we're going to do is, remember that we kind of discussed this a little bit last time. If you remember, the mass percent of a compound is an intrinsic property. It doesn't matter how much of that compound you have, whether you have one molecule of the compound or a huge pile of the compound. The mass percent is always going to be the same. It's an intrinsic property. It doesn't depend on how much you have. So we can assume any amount of compound that we want and find the mass percent. Or find the empirical formula. And so what we have here is, if we're given percentages, we'll just assume that we have 100 grams of the compound. So if we're given mass percents, assume 100 grams, and then what that means is that the mass of each element in 100 grams is equal to those percentages directly, so you don't have to do any conversions. So when we worked the other way last time, when we took the chemical formula and converted it to mass percent, The way we did that is we assumed 1 mole of compound because the molar mass gives us the mass of 1 mole of compound. Here, if we're giving you mass percents, well, it's easier to assume that we have 100 grams of compound, and then what that means is that in that 100 grams, we have 15.94 grams of boron and 84.06 grams of fluorine. The percentages equal the mass out of 100 grams. Okay, so that's what we're going to do for mass percents. We're going to assume that amount. And so from there, now we're ready to just do the same conversions. We find the moles of each element, where if we're assuming 100 grams of compound, we'll have 15.94 grams of boron, and we'll convert to moles by dividing by the molar mass. So 1 mole of boron is how many grams? That comes from the periodic table. Boron we dealt with a little bit also earlier. It's 10.811. That's the number we get for boron. Or just 10.81 is enough precision for this, no problem. So we divide by the atomic mass and we get 1.474 moles of boron, and then we do the same thing for fluorine, where we use its mass percent, which we found by difference, and assume that out of 100 grams of compound, that's how many grams of that element there would be. Definition of mass percent. Divide by its atomic mass, which I'll spare you from flipping back and forth too many times, but that's going to be exactly 19 for fluorine. If you look that up in the top right of the periodic table, 19 grams per mole for atomic mass of fluorine. So grams cancel out because it's in the moles of each element, which is in this case 4.424. All right, and then the last step is to normalize to get them down to the smallest ratio. So we have B 1.474, F 4.424, which is a non-standard way of writing a formula with all these decimals. So we divide both of them by the smallest, which is 1.474. And again, this is another one where we get whole numbers directly. We get just BF3. And we don't have to do any further manipulation of that. All right, so it's really the same steps. It's just that we're giving you mass percents. You assume you have 100 grams, and then the percentages just become masses. And also recognize that sometimes you'll have to find one or more, well, really just one of the mass percents by difference, as we did here. If you don't have all of them, you have to use a little bit of extra effort at the beginning to do that. All right, so any questions on that? Now, the last step of this is what do we need to do to determine the actual molecular formula? Because this approach here of using masses of elements or mass percents and then finding, the empirical formula just gives us that smallest whole number ratio. But what if we want to know what the actual molecular formula is? So the way that you do this is you need one other piece of information, which is the molecular mass. So you're going to use the approach that we've just developed to find an empirical formula, but if you want to convert that empirical formula into a molecular formula, then you need to figure out also what the molecular mass is. So there are separate measurement techniques for doing that, and so the molecular mass by itself won't identify the formula, but the molecular mass with the empirical formula allows us to do that. So here's an example where we determine that the empirical formula of a compound is CH2, and there are millions and millions of compounds in the world that have the chemical formula or the empirical formula CH2. Pretty much if you ever heard of polyethylene plastic or polypropylene, those are basically all CH2 as their empirical formula. So what would be the molecular formula? Well, there's a lot of possibilities. So what we have here is the empirical formula and the molecular mass. So what you're going to do is recognize that the molecular formula is going to be some whole number multiple of the empirical formula, which also means then that the molecular mass is going to be some small whole number multiple of the empirical formula. So usually in problems like this, we will give you the molecular mass. Here we're also giving you the empirical formula, but a lot of times you'll have to find this. And then so if you have those two pieces of information, we can do it. So what we're going to do is for this empirical formula that we have, which we are given here or we would find using the approach we just learned, you're going to calculate the empirical mass, which is just the sum of the atomic masses from the empirical formula, same way that we would calculate molar mass. So our empirical formula has 1 carbon, which has a atomic mass of 12. For this, we usually just need to do whole numbers. We don't really need to go too detailed, but it'd be 12 AMU for carbon if we really want to be exact, 12.01. That's the number from the periodic table. Again, AMUs, grams per moles, are kind of interchangeable. And then we have 2 hydrogens in the empirical formula, and the atomic mass of hydrogen is 1.008 AMU, or grams per mole. So that's hydrogen. So we're just going to add those up to get the empirical mass, which is, we'll just do it approximate here because we're only given the molar mass in a whole number form, 14 AMU. All right, so once you have the empirical mass and the molecular mass, you're going to divide the two to figure out what is the factor that relates the empirical formula to the molecular formula. So that's the next step, is to divide the two. Molecular mass over empirical mass. So the molecular mass is given as 70 AMU. We just found an empirical mass of 14. And so that factor is going to be 5. And so what this tells us then, by doing this ratio, yes?
Why is it 14 instead of 24?
Because it's 12 plus 2.
Sorry.
Yeah. So CH2, not C2H. Yeah. All right. So then you're going to divide the two. So 70 divided by 14 is 5. And that tells us then that the molecular formula is a factor of 5 bigger than the empirical formula. And so what we're going to then do is say, okay, our molecular formula is, the empirical formula is CH2 taken 5 times, multiplied by 5, which is C5H10. So this would be the molecular formula of this compound. It has an empirical formula of CH2 and a molar mass or molecular mass of 70. And those two together can uniquely identify it as C5H10. So that's the only way that you can get all the way to the molecular formula, is you also need then the molecular mass as part of that. All right, so it's just figuring out the relationship, the factor that relates the molecular and empirical formula, and then multiplying the empirical formula by that factor to get the molecular formula. So any questions on that? So that's kind of the next exception you could do. So I think we have one more example that puts both of these together, these concepts together. So we have this compound that has 28.18% mass manganese, 30.8% carbon, and 41.03% oxygen. Those are all mass percents. And we're giving you the molar mass of 389.98. So what is the molecular formula? So the steps are going to be, first we can find the empirical formula. If we have mass percents, we assume 100 grams of the compound. And then that tells us that the mass percent of each element would be the mass of each element in 100 grams. So with those mass percents directly used as masses, we're going to find the moles of each. So for manganese, it's 28.18. And then we're going to divide by the atomic mass of manganese to get it into moles. I think that one is 53.94, but let me check. So Mn, or sorry, I got that one, 54.94 is Mn. So that's number 25, and that's the atomic mass, 54.94. So grams cancel, and that gets us into moles, which is 0. I recommend not doing too much rounding in these problems until the end. So if we're giving you 4 significant figures for the masses, keep all 4 as you go through. Don't try to lop things off too much. You might make rounding mistakes. For carbon, which is the next element, we have 30.80 grams from the mass percent of 30.80%. And we divide by the atomic mass of carbon, which is 12.01, which we've used many times already. So that's going to be 2.564. And then finally for oxygen, it's 41.03%, so 41.03 grams of oxygen in 100 grams of that compound. Atomic mass of oxygen is 16 once again. So when we divide that number by 16, we get the same number we got for carbon, 2.564. All right, so we're following those same set of steps to get the moles of each element, and then we can find the empirical formula. We have let me just round it a little bit now because I'm getting tired of writing all these decimals, but 3 decimals should be enough for getting these ratios correct. Carbon is 2.56, oxygen is 2.56. And so we divide those by the smallest one, which is 0.513, the number for manganese. So we're getting these down to a small whole number ratio. And so what we get is MnC5O5. All right, so that's going to be our empirical formula. When we use the mass percents or the masses of the elements that are given to us, that's going to just give us empirical formula. It's possible that this is also a molecular formula, but what we need to do now is compare the empirical mass to the given molar mass to figure out what the relationship between those two is. So now we're going to calculate the empirical mass, which is just calculating what would essentially be the molar mass of the empirical formula. And so what that comes out to is we have 1 manganese in the formula, which, as we saw above, has an atomic mass of 54.94. And then we have 5 carbons in the formula, which has an atomic mass of 12.01, which we used above as well. And 5 oxygens, which has an atomic mass of 16, also given up here. So that empirical mass comes out to 195 grams per mole, or AMU if you prefer. And then finally what we're going to do is we're going to divide the two. So the molar mass, barely enough room for this problem, a lot of steps. Molar mass divided by the empirical mass. The molar mass is given as 389.98. So they're clearly not the same. So the empirical formula is not also the molecular formula. The empirical mass is 195. And so when we divide those two, we basically get 2 as the factor. Again, it might be like 2.00 something, but it's close enough to 2. And that tells us that our molecular formula would be 2 times the empirical formula, because the molecular mass is 2 times the empirical mass. So we're going to double this to get the molecular formula, which is Mn2 C10O10. All right, so this doesn't tell us anything about the structure of the molecule, but it tells us how many of each atom would be in the formula for one molecule of that compound. All right, so that's about as complicated as it gets of determining molecular formula using mass percents to get the empirical formula, and then the additional step of comparing the empirical formula to the molecular formula using their respective molar masses. All right, so any questions on that? Yeah.
Does it matter what order we put the elements in the formula?
No, I mean, if it's multiple choice, obviously it'll be clear from the answer choices, but in reality it doesn't. I mean, we learned some things in chapter 3 about what order to put things in for certain classes of compounds, but in problems like this, it's not usually obvious what kind of compound it is, so you would just put them in whatever order they're given to you. Or we might specify which order to put them in if we're actually having you type in the formula. But yeah, it's not going to be an issue, I don't think. And it really doesn't matter. All right, any other questions? Okay, so let's go on then to another related topic. It's really the same thing that we're doing, but just it's a more roundabout way. But the reason that we teach this is because, you know, this is actually how it's often done in a sort of a real research setting. So you might be wondering, like, well, how do we actually figure this out? You know, how do we know what the mass percents of the elements are? How do we, you know, do it experimentally? Well, one way to do this is called combustion analysis, which is usually it's done on organic compounds, so compounds that are mostly carbon, hydrogen, oxygen. Sometimes other things can be in there as well. And what you do is you set this compound on fire. You burn it, and it's kind of, as a researcher, sometimes it's unsatisfying because you put your blood, sweat, and tears into making these compounds, then you just set them on fire after you're done. So it's not fun, but you don't need a lot of the compound, which is nice. Usually a few milligrams is enough. But what you do is you burn it, and then we haven't talked a lot about combustion reactions yet. We'll see that a little bit more later this chapter. But when you burn something, all of the carbon, ideally anyway, it doesn't always work this perfectly, but ideally all of the carbon in the compound will be converted into carbon dioxide as a combustion product. So when you burn something, you release a bunch of CO2, and all of the carbon from that is going to be converted into CO2. All the hydrogen that was in the original compound would be converted into water. H2O is the other combustion product. So when you're burning something, you're doing it in the presence of oxygen. So there could be oxygen in the compound that ends up in these products, or there could be, and then you're also going to be having oxygen in the air that's present while you're burning it. So oxygen is involved as well. And so then if your compound has other elements in it, you may form other combustion products as well. And usually if you have other elements besides carbon and hydrogen, in a combustion analysis, you'll get their masses by difference. So you'll know how much mass of compound you started with. You'll figure out how much mass of carbon and hydrogen is in there based on how much of the products form, and then whatever's left over has to be the other stuff. So that's usually done by difference and not really as directly as the other two. So anyway, what we're going to do then is we're going to find the mass of CO2 that forms. We're going to use that to find out how much mass of carbon was in the original compound. We're going to measure how much water is produced and use that to figure out how much mass of hydrogen is in the original compound. And then for anything else that's there, which is often just going to be oxygen, but sometimes another element besides oxygen, you're going to do that by difference. So you're going to know the total mass of the compound that you started with, and you're going to subtract the mass of carbon, subtract the mass of hydrogen that you found, and that will give you the mass of anything else that's in there besides carbon and hydrogen. So this combustion approach will always allow you to figure out the masses of carbon and hydrogen or the respective mass percent. For other stuff, if there's one other element, you can do it because you can just do it by difference. If it's more complicated than that, then this technique is not always as useful. But for us, it'll always work out fine for the types of problems we'll do. So the advantage of combustion analysis is that it allows us to determine the empirical formula. It's a more indirect way of getting there, but experimentally it's a pretty powerful technique for determining the empirical formula. And just as a little bit of an aside, not that this is important for you guys, the way this is usually used in a research setting is not that we, do combustion analysis on something where we have no idea what the empirical formula is. Usually we think we know what it is, and we're using the combustion analysis to confirm that. So we have what we think our molecular formula or empirical formula is, and then we figure out the mass percents of the elements using combustion analysis and compare that and see if they match up to each other to tell us that we've made what we think we're making. But it's a powerful technique for determining or confirming empirical formulas of compounds. All right, so let's see how this works. These problems take a lot of they're tedious, let's just say it that way. So you're going to want to make sure that you're proficient at doing this. Okay, so what we have is a compound consisting of carbon, hydrogen, and bromine. So in this compound, bromine would be the other stuff, the stuff that's not going to be involved in forming the combustion products directly. So we have carbon, hydrogen, and bromine in this compound, and we analyze it by combustion. So we're taking 5 grams of the compound, which in reality you don't have to burn anything close to this amount usually, but for this problem it's just simpler to work with grams. So 5 grams of compound is burned, and it produces 0.871 grams of CO2 and 0.179 grams of water. What is the empirical formula? So in a combustion analysis, this is typically what you're going to do. You're going to know how much compound you're burning. You measure that out ahead of time. You measure how much carbon dioxide and water forms, and that's going to be sort of your output. And we're going to use all that information together to find the empirical formula. So in problems like this, if the compound only has carbon and hydrogen, then you can go just straight forward and calculate the moles of carbon, moles of hydrogen, and get your empirical formula. It's a little bit simpler. But if it has another element involved, like we do here, bromine or often oxygen is even more common, then what you have to do is you also have to find the masses of carbon and hydrogen as part of your solution to the problem. So that's what we're going to do first here. We're going to end up sort of undoing some of this effort later on, but we have to find it. We have to find these anyway. So let's do the mass of carbon first. So there are different ways of setting this up, but typically what we're going to do is we're going to start with the mass of CO2, because all of the CO2 that forms contains all of the carbon that was in the original sample that we burned. So we start with the mass of CO2 that we're given, 0.871. And just like we've been doing in all of this whole chapter, when in doubt, convert to moles, because the chemical formula of CO2 tells us that there's 1 mole of carbon per 1 mole of CO2, so we can convert to moles, then we're on our way to finding how much carbon is in there. So we'll convert to moles first. So we need the molar mass of CO2, which is a compound. So that's going to be carbon, which is 12.01. Again, I'm looking these up in the periodic table. I'm not going to flip back and forth a million times. So that's, and then plus 2 oxygens, which are 16. So the molar mass of CO2 is carbon plus 2 oxygens, which is 44.02. So that's the number we're going to use down here, 44.02 grams of CO2 in 1 mole. All right, so that gives us the moles of CO2. And then from there, we can find the moles of carbon. And that comes just from the chemical formula. CO2 has a subscript of 1 by carbon, or no subscript, which implies a 1. So that means there's 1 mole of carbon for every mole of CO2. All right. Now, as I said, if the compound only had carbon and hydrogen in it, we could stop here because we're going to need the moles of carbon eventually. But for this problem, we also need the mass of carbon, so we're going to have to go one more step. So this is going to give us the mass of carbon by using the atomic mass. So we want moles to cancel, and we'll convert that back into grams. And so we're going to use the atomic mass of carbon, which is 12.01. 12.01 grams of carbon in 1 mole gives us back into grams of carbon. So we get 0.238. All right, so that's the mass of carbon, which we'll eventually need also to find moles, but we're going to stop there for now. We'll do the same thing for hydrogen. And so for hydrogen, all of the hydrogen that's in the compound is going to end up in water as a combustion product. So we start with the amount of water that we have, which is 0.179 grams. We convert that to moles first. So 2 hydrogens and 1 oxygen gives us a molar mass of 18.02 for H2O. If we're being nice to you, we'll give you the molar masses that you need so you don't have to calculate them yourselves, but we're not always nice. So you get 18.02 for water, but you'll use CO2 and water all the time, so those will become familiar. And then the only difference here with hydrogen is if we're going to try to find the moles of hydrogen next, we have to be a little bit careful here, and this is where writing things out and being very cautious about labeling things is helpful, because if we look at the chemical formula here for H2O, there's 2 moles of hydrogen in 1 mole of water, because there's a coefficient or subscript of 2 there next to H. So we have to double this to figure out how many moles of hydrogen there are. Okay, the moles of water, it's going to be 2 moles of hydrogen for every 1 mole of water. And then, as I said, we need the mass of this for part of this. We're going to go one more step and use the atomic mass of hydrogen, which is 1.008 grams per mole, to figure out how many grams of hydrogen we have. So that ends up being a relatively small number, but it's going to be 0.0200. All right, so that's the mass of carbon, that's the mass of hydrogen. As I said, if the compound only had carbon and hydrogen, you could stop here at moles, but we're going to need the mass as well. And then finally, to find the mass of the other element, which is bromine, and this is why we needed the masses of carbon and hydrogen, it's going to be done by difference. So we have 5.00 grams of our compound that we burned. That's given to us in the problem. 5.00 grams is burned. We just determined from the CO2 product that we have 0.238 grams of carbon, and we have 0.02 grams of hydrogen. And so by difference, we'll find out how much mass of the other element is in there. And again, this is what you'd have to do for anything except for carbon and hydrogen. Carbon and hydrogen we can find directly based on the masses of CO2 and water, but anything else that's in the compound, oxygen, bromine, nitrogen, whatever it is in that case, you have to do it by difference like we're doing here. So we just subtract and we get 4.74 grams of bromine. So by mass, most of this compound is actually bromine, but those are going to be the masses of each element. All right, so that was a lot of effort to get there, but now we have the masses of each element, so we know how to find the empirical formula now once we have the masses of each element. We're going to follow the exact same steps that we've been doing since the beginning of today. All right, so we have masses of each element we're going to convert to moles, and this is our first 2-pager, I think, the way to have 2 pages to do all this. And so the moles of carbon, we're going to use the mass that we were, so we're basically undoing the last step of the conversion we did above, where we have grams of carbon. Now we're going to convert it back into moles, this time by dividing by the atomic mass. So if you prefer, you might find it more efficient when you do these types of conversions is, stop here and get the moles of carbon first, and then just multiply by that to get the grams. But you're going to need both of them either way. So whatever order you do that in is fine, but you're going to need the grams and the moles of carbon for this problem. So now we're going to just undo that last step and find moles of carbon using the atomic mass, which is 12.01, dividing. So we get 0.0198 moles of carbon. And then for hydrogen, the atomic mass is 1, so this one we could probably just do in our head, not have to do out as precisely. But just to remind you of the steps that are involved, you're going to take the mass of hydrogen that we found above, and then you're going to divide by the atomic mass to figure out how many moles that would be. And again, since the atomic mass of hydrogen is basically 1, you're going to get almost the exact same number, so you don't really need to do that math explicitly if you don't want to. Whether you use it as 0.02 or 0.0198, it's not going to affect your final answer. And then finally for bromine, which is the other element, we found its mass by difference. And we're going to use its atomic mass to convert into moles. So that one we haven't used yet, so let's look it up. Bromine is over here, number 35, one of the last elements you need to know by symbol. So 79.9 grams per mole is the atomic mass of bromine, which we'll use in this last step here. So 79.9 grams in 1 mole. So we divide by the atomic mass to get moles of the other element, which comes out to 0.0593. All right, so we have moles of each element, and now to get the empirical formula, we just have to divide by the smallest one. So we have carbon 0.10198. Hydrogen, same number. Bromine, 0.0593. And we're going to divide all of those by the smallest, which is 0.0198. And what that comes out to is CHBr3. So that's the empirical formula. That would be the molecular formula for a compound called bromoform, which is just chloroform, but with chlorine, with bromine instead of chlorine. So CHBr3 is what we come up with for that. All right, so you're gonna, once you have masses of each element, then the problem becomes what we've already done a few times today. But for combustion analysis, it does take a bit of effort to get there. Yes?
What do you do if there's more than one, like...
If there's more than one other element besides carbon and hydrogen, we need to either tell you at least the mass of one of those directly, or maybe tell you that all of it is, converted into this other compound, and then you extract the mass like we did for, CO2 to carbon and H2O to water. We have to be given some other information if there's more than one. You can't just, you wouldn't be able to do that. But I don't think it'll ever be more than one for the problems you'll do, because as you saw, even with just 3 elements, it's a lot of work. So it'll probably just be a hydrocarbon, which is carbon and hydrogen. I guess that's a term you should start to be familiar with a little bit. If you see hydrocarbon, that tells you that it's just carbon and hydrogen. This one is not a hydrocarbon because it also has something else, so there might be one other element that you have to deal with like we did here, but I don't think it'll be any more complicated than that. All right, any questions? All right, so that's not the most fun type of problem, but it is one that you're going to see from time to time. All right, but what we're going to move into now is we've talked about mole relationships and how that sort of involves individual compounds and how we can relate mass and moles for both elements and compounds and all this stuff. Now we're going to start talking about reactions that involve converting one substance or group of substances into another group of substances, and how we can then calculate how many, the amounts of each substance that would be involved in that reaction. So the first thing we have to do is we have to learn how to set up and balance chemical equations. And so, a chemical reaction is a situation where the atoms and elements and or compounds are reorganized to form new substances. So we've kind of referred to these a little bit, but you basically have some starting, mixture of substances. They combine with each other chemically, rearrange, form new bonds, all this stuff, and they form a new, combination of substances on the other side. So the way that we arrange them in a chemical equation is on the left side we show the reactants, and these are going to be elements and or compounds that are consumed in a chemical reaction. And they're always going to be on the left, as we'll see. And then on the product side, we're going to have elements and or compounds that are formed as products, that are formed during the chemical reaction. And those are going to be on the right side of the chemical equation. And then each reactant and product, they're going to be indicated with their chemical formula, which is just, a single atom if it's an element, or some formula if it's a compound of multiple elements. But each of those substances on the left and on the right side is going to have a coefficient in front of it. And so these are going to be numbers that are in front of each chemical formula or symbol. And what they tell you is the ratio in which everything reacts with each other. So it's going to tell you the number of, so you can sort of think about it at the atomic level, the number of atoms or molecules that are involved in the reaction. But the more useful way for us to think about it is in terms of moles, the number of moles of each substance that reacts or is formed in that equation. And so that's what the coefficients tell you. And so it tells you, you can think about it at the atomic level. This many molecules of one substance reacts with this many molecules of another to form this many molecules of the product. You can think about it in that terms, but the way that we're usually going to think about it in this chapter is in terms of moles. This many moles of one substance reacts with this many moles of another to form this many moles of products. And in terms of how we determine what those coefficients are, what we have to remember is one of the first mass laws we learned, conservation of matter, or conservation of mass, which is that atoms are neither created nor destroyed during a chemical reaction. So however many atoms of one type you have on the reactant side, you have to have the same number of atoms or the same moles of that atoms on the product side as well. So we're going to have the same collection of atoms on each side, just rearranged and forming different compounds or different substances. All right, so that's kind of the basics of what's in a chemical equation. So let's talk about now the steps for balancing them. So there are going to be, problems that just involve balancing a chemical equation. Chapter 6, we're going to cover more types of chemical equations and how to balance them as well. But then also for a lot of the numerical problems we do, the starting point is always going to be a balanced equation, so you have to do that as part of that as well. All right, so let's talk about chemical equations and how we balance them. So first we're going to arrange the reactants and the products. As we kind of already said, we're going to put reactants on the left, products on the right, with an arrow in between them. All right, and then what we're going to do is we're going to add coefficients. Now sometimes when you're adding coefficients, depending on how complicated the chemical equation is and how many different reactants and products there are, a lot of times it becomes almost like a guess and check method where, okay, I'll put a coefficient here, but then I have to change the coefficient over there. And you kind of just keep going back and forth until everything is balanced. But usually what's helpful is, an approach that I like to follow is figure out what your most complex substance is in the reaction, the one that has the most atoms in the formula, or the most different types of atoms, and just set one of those to a coefficient of 1 and try to balance everything else off of that. This won't always work perfectly, but it's usually a good starting point if you're unsure of where to start. Is find your most complex substance and set its coefficient as 1. Just like in chemical formulas, we don't usually explicitly show coefficients of 1, but you can put it there and it's not wrong to have it there. And that'll just remind you that, okay, this substance, we're going to keep it as a coefficient of 1, and we're going to try to balance everything else off of this, and not just that one. That's usually helpful to do. And then what you're going to do is you're just going to adjust the coefficients on both sides to make sure that the atoms balance. Now, when possible, you want to use whole number coefficients. It's not wrong to use fractional coefficients, but usually if we're asking you to balance an equation, and that's really the whole thing you're doing in that problem, we'll specify that you should balance it with the smallest whole number coefficients. That's conventionally how it's done. If you don't use whole number coefficients, as long as it's balanced, if you're using that as part of a numerical problem to do some sort of stoichiometry calculation that we're going to learn in a little bit, if that's the case, then you're okay if you don't have the smallest whole numbers. But usually if we ask you to balance, that's what we want you to do. Another thing that's helpful, as we'll see when we do this, is as you're adjusting coefficients on each side, you're going to have to sometimes change that on one side, and that's going to affect what you do on the other side. try to find the elements that only appear once on each side of the equation. So if I only have carbon in one substance over here and carbon in one substance over there, well, then you can pretty clearly see what their coefficients need to be to make sure that they're balanced. If a substance appears more than one time on one side of the equation, then sometimes it's a little bit unclear what the coefficient should be, so you want to usually save those for the end. So that'll become clear as we do some of these. And then finally, it's good to check yourself. Make sure that the number of atoms on the left of each type equals the number of atoms on the right. So we're not creating or destroying atoms. We're not changing one element into another. We're not doing alchemy here. We're doing chemistry. And so you have to make sure then that everything balances out. And it's good to check yourself after you think you're finished, just to make sure that you didn't miss anything. Another thing that will sometimes be shown in chemical equations, it's not a big deal for balancing them, and it's not a big deal for for what we'll have to do. But just so you're aware of this, is sometimes the states of matter will be sort of specified for each reactant product. There'll be a little parenthetical letter next to it that tells you what it is. So S would be solid, L would be liquid, G would be gas. There's one other one we're going to cover in one other abbreviation like this that we'll cover in Chapter 6. And for some of the stuff that we do in Chapter 6, and I guess later on even in Chapter 8, those states of matter become a little bit more important for what we're doing. For our purposes, if we're just balancing, they might be there, so don't be confused by them, but they don't really affect how we do anything at this stage. All right, so let's go through a few examples and show how to balance them. So here is an example of a combustion reaction. So we talked about combustion analysis just a little bit ago, and so this is what's happening when you burn something. This is a hydrocarbon, there's carbon and hydrogen. So as we said, you burn something in the presence of O2, that's your other reactant, and I only put gas next to this one. These should all be gases, I suppose, but who cares? Just pretend it's not there. All right, so anyway, you burn it in the presence of oxygen, and you form carbon dioxide and water as the products, as long as it's only carbon, hydrogen, and oxygen that are in the reactant, which is what we have here. So that's the reactants and products. Now, as I said before, what I usually like to do for these is figure out what the most complex substance is and set it to a coefficient of 1 initially. And so that one here is going to likely be this C2H6. It has 8 atoms in the formula. Everything else only has 2 or 3 atoms in the formula. So the one that has the most number of atoms in the formula, this one has 2 carbons, 6 hydrogens, a total of 8 atoms in the formula. Let's set that to 1 initially. And even though you don't really write coefficients of 1 usually, we'll just put it there to remind ourselves that that's what we're using for now. And then from there, the next thing you want to do is you want to find elements that only appear once on each side of the equation. So if we look at oxygen appears once on the reactant side, but it appears in both products. It appears in both CO2 and water. So I wouldn't recommend trying to balance oxygen first, because there's going to be a lot of combinations of coefficients that would work to keep oxygen balanced with a coefficient here, and then whatever coefficients here would end up balancing that. So you don't really want to start with something that appears more than once. Find something that only appears once. So carbon and hydrogen would both work. Whichever one you start with is fine, because carbon we have only in this reactant here, C2H6, and only in this product here, CO2. So we can balance that one first. So if our reactant has 2 carbons in it, we also need 2 carbons on the product side. CO2 only has 1 in the formula, and so we're going to put a coefficient of 2 in front of it to make sure that we have 2 total carbon atoms on the right side of the equation. We don't want to modify the formula of the compound. That's going to change the identity of the substance altogether, but we put coefficients out front to tell us how many molecules or how many moles of that compound are involved. So by putting a 2 there, we have 2 carbons here and 2 carbons there, so those are balanced. And then for hydrogen, likewise, it only appears once on each side. This has 6 hydrogens, so we need 6 total hydrogen atoms on each side. Water only has 2, so if we want to have 6 total hydrogen atoms, we need to put 3 in front of water to balance out the number of hydrogen atoms. So once we've set these coefficients, we don't want to change them, because if we change any of the 3 that we've put in there already, everything's going to get all out of whack. So the only thing left to figure out is how many oxygens do we need on the left side. So over here on the right side, we have, for oxygen, 2 times 2, 2 carbon dioxides with 2 oxygens each is a total of 4. Then we have 3 waters, each with 1 oxygen in the formula, so that's another 3. So we have a total of 7 on the right. So right now our equation has 7 oxygen atoms on the right. We also need 7 on the left. So if we have O2, which has 2 oxygen atoms, we need 3.5 O2 molecules to make a total of 7, or 7 over 2. So a coefficient of 7 halves, we have 3.5 or 7 halves, 2 oxygen atoms in each molecule, total of 7 on the left as well. So this would be a valid balanced equation, but usually when we're doing this, as we said, we're going to specify that you want to use the smallest whole numbers. I didn't specify that here, but that's typically how it would be set up on a homework question or exam. So what we want to do then is we want to adjust all the coefficients to make them whole numbers. So here we have a coefficient with a denominator of 2, so we're going to double everything to get rid of that fraction. But when you adjust the coefficients in this way, you have to do the same thing to all of them, because if you just do it to one of them, you're going to throw off the balance again. So we're going to double every single coefficient here to get rid of this fraction. So 1 times 2, that becomes a 2. 7 halves times 2, that becomes a 7. 2 times 2 becomes a 4. 3 times 2 becomes a 6. So if you have to adjust the coefficients to get whole numbers, that's totally fine, but you have to make sure you do the same adjustment or the same factor for every single coefficient, otherwise all the hard work you did to balance everything is going to be evaporated. Okay, so that's how we would approach that one, and now we can check ourselves to make sure that we have the right amount of atoms on each side. So let's do carbon first, on the left side and on the right side, reactants and products. So for carbon on the left, we have 2 times 2. We have C2H6 has 2 carbon atoms, and there's 2 molecules of that, so that's going to be a total of 4. On the right side, we have 4 CO2s. Each one has 1 carbon, so that's also a total of 4. So that checks out. And then for hydrogen and oxygen, let me do them over here to give myself a little bit more room. So we have hydrogen next. We have, on the left side, we have 6 hydrogens in this molecule, but there's 2 of them from the coefficient, so 2 times 6 is 12. And then on the right side, we have 6 waters, coefficient of 6. Each one has 2 hydrogens in the formula, so 6 times 2 is also 12. And then for oxygen, this is the slightly more complicated one because it appears multiple times on the right side. But on the left side of the equation, we have 7 O2s. 7 times 2 is 14, so we have 14 oxygen atoms. 2 oxygen atoms in each O2 molecule, 7 of them total. And then on the right, we have 4 CO2s with 2 oxygens each, plus 6 waters with 1 oxygen each. So 8 plus 6 is also 14. All right, so that allows us to check our work and make sure that we have the same number of atoms on each side. So we have 4 carbon atoms on each side of the equation, 12 hydrogen atoms, 14 oxygen atoms, smallest whole number coefficients. So that's going to be the best job we can do in balancing that equation. All right, so we have any questions on that? So this is something you'll just have to, like most things in this course, practice a lot. You'll get the hang of it, and most of them are not too bad. All right, so the next one here is another one where we're going to actually, we're not always going to give you explicitly the reactants and the products. Sometimes we will describe them in the problem, and you have to know how to figure out their formulas based on things we've already learned about chemical formulas. So here we have Fe2O3, which is the formula for rust. As we probably know, that's going to be formed by the reaction of iron with oxygen gas. So what's the balance equation for this formation? All right, so if it's an element iron by itself, the formula is just going to be the symbol for that element, which is just Fe for iron. So that's going to be one of our reactants. So it's reaction of iron and oxygen. So those are our 2 reactants, iron and oxygen, which is formula of O2. And it's going to be forming rust, which is Fe2O3. So we have to get a little bit of the hang of, converting names into formulas and identifying reactants and products from a word problem like this. But whatever is formed is the product, and whatever is reacting will be the reactants, of course. Those will be on the left side, products on the right. So we're going to arrange things in that way. Okay, so that's what our starting point is, but now we have to balance it. And again, it's helpful to set the most complicated thing to 1. So this is our most complicated substance. It has 5 atoms in the formula, 2 different elements. Everything else is an element. So we're going to just set that to 1. So we can balance then each element on the other side from that. So we have 2 irons on the right side, Fe2. So we're going to need a coefficient of 2 there. We always just add coefficients. We don't change subscripts again that'll affect the chemical formulas. And then here we have 3 oxygens on the right. So similar argument as last time, if we need 3 on the left, we need a coefficient of 3 over 2, or 1.5. 1.5 times 2 is 3 oxygens on both sides. If we wanted to be in whole numbers, which we usually do, then we have to do the same thing we did last time, which is double them. So we're going to double this whole thing. And what that's going to lead us to is 2 times 2 is 4 for iron. 3 halves times 2 is 3 for O2. Then the product side, 1 times 2 is 2 for the rust, Fe2O3. All right, and we can check that our reactants and products have the same number of each atom. So for iron, we have 4 Fe, which is just 4 iron atoms, or 4 moles of iron on the left side. And then the product side, 2 Fe2O3. So 2 of those with 2 irons each is also 4. So that checks out. And then for oxygen, we have 3 O2. So 3 times 2 on the left, 6 oxygen atoms on the left, 2 Fe2O3. So each of those has 3. There's 2 of them. So 2 times 3 is 6 on the right. So we have the same number of iron, same number of oxygen on each side. So the only difference here, this is actually an easier equation to balance, but sometimes we're going to require you to take some information from the problem, converting names to formulas from at times, and also make sure that we can arrange the reactants and the products on the correct side based on how it's stated in the problem. So you'll have to get, again, used to that a little bit, but there will be times when that's going to be required. So any questions on that one? All right, the last one we'll do, it looks very complicated, but as we'll see, it ends up not being too bad. So we have this very complicated formula, cesium-4, rhenium-6, selenium-8, I6. Is formed by taking rhenium metal, selenium, cesium iodide, and iodine, I2, and just blasting them at 800 degrees Celsius for 4 days. So we want to know what is the balanced equation. And then sometimes the way that this problem is set up is just sort of to simulate what you might see on Blackboard. A lot of times we don't ask you to, put the whole balanced equation. Obviously that's hard to do in Blackboard. So we'll usually ask you for what is the coefficient on one of the reactants or one of the products, or as we did here, sometimes we'll ask you to just determine the sum of the coefficients on one or both sides of the equation. Again, it's not a very useful number to actually know, but it's just a way for us to enter the answer in Blackboard in a sort of objective, easy to grade way. So just follow the directions closely when it asks you to do that, even though knowing that number is not going to really be useful in any chemistry context. Now, the reason that I gave you this example here, in addition to it being a little bit more complicated than some of the last ones, but this compound here has a special place in my heart because it was the first compound I made in my undergraduate research lab. So they always say you remember your first chemical reaction. This was mine. So anyway, this is the product, and then here's the 4 different reactants we used to make it. So we're going to take rhenium Re. I had to do this down low enough so I don't run into the picture there. And give myself a little bit of room in front of that. There we go. All right, rhenium, selenium, Se, cesium iodide, CSI, and iodine, elemental iodine, I2. Heating those together, believe it or not, miraculously forms this complicated compound here, cesium-4, rhenium-6, Se8, I6. All right. Now, I think it's pretty obvious in this case what the most complicated reactant or product is. I don't think we have to argue about that one here. So it's going to be that one. So we're going to set that to 1 and then make sure everything else balances off of that. Now, as I said, you want to first start with the elements that only appear once on each side. Well, every element only appears once on the product side because there's only one product. But if you look at iodine, we don't want to start with that one because iodine appears both in cesium iodide and I2. So we're not going to really know how much of each of those we need to total up to 6 iodines originally. So let's balance the other 3 elements first because cesium, rhenium, and selenium only appear once on the reactant side. Rhenium here, selenium here, cesium here. Okay, so cesium-4, we need 4 of those, so we're going to put a 4 there. Rhenium, we need 6 of them, so we're going to put a 6 in front of rhenium. Selenium, we have 8 in the product, so we're going to put an 8 there. All right, so that's going to be those 3 things balanced. Now we just have to make sure that iodine is balanced to finish this out. So we have 6 iodines in the product. We had 4 here from cesium iodide, so we need 2 more. Well, I2 already has 2 iodines in it, so we just need a coefficient of 1 in front of that. Again, it wouldn't normally be written, but that's what it's going to be. So we're going to balance that one last because we use cesium iodide to balance cesium. That gave us 4 iodines. We need 2 more. We don't want to adjust this coefficient anymore because that's going to undo our balancing of cesium, so we just need a coefficient there to make sure that that is worked out correctly. So if we check ourselves, there's the same number of elements on each side. And then this asks for the sum of the coefficients on the reactant side. So on the reactant side, we have 6 in front of rhenium, 8 in front of selenium, 4 in front of cesium iodide, and then even though it's not often written, we have to remember that there is an implied coefficient of 1 in I2. It would be written like that most often, but there is an implied coefficient of 1 there, even if it's not stated directly, and that gives us a total of 19. So if you're asked to do coefficients or report coefficients as part of your answer, make sure you don't forget about those implied coefficients of 1, which won't be shown, but if you don't see anything in front of it, that means the 1 would be there if you're writing it out explicitly. All right, any questions on that? All right, so what we're going to close with the little bit of time we have left today is just a quick introduction to stoichiometry. We're not going to get as far as I was hoping today, but that's okay. We'll pick it up next time. And so stoichiometry is where we're going to use all of the stuff we've been doing up until now, building this up, relationships between mass and moles, other relationships involving moles that we're going to get in a little bit. And we're going to use those to calculate the amounts of reactants and or products involved in a chemical reaction. So, how much of this reactant is needed in the chemical reaction, or how much of that product is formed in the chemical reaction. Stoichiometry allows us to calculate those amounts where we need not only the identity of the substances, but also the balanced chemical equation is a key part of that. So the key concept here is what's called a mole ratio, and that's what the coefficients in the balanced chemical equation tell you. So we can interpret them in terms of individual molecules, but the more useful way for us, especially in stoichiometry, is to recognize that they tell us the relative numbers of each moles of substance that are involved. So the coefficients in the balanced chemical equation what they tell us the relative numbers of moles of each substance in the reaction. All right, so as an example, in a very generic sense, let's say we have this chemical equation here, not even using real substances for the moment. 3A plus 2B forms 4D. What we can generate from any balanced chemical equation is a whole bunch of conversion factors that allow us to convert one amount of substance into an amount of another using the coefficients, the numbers that are out in front. So we can write all of these different ratios. For example, 3 moles of A are going to react for every 2 moles of B that react. So that would be a ratio between how many moles of A and how many moles of B are reacting with each other. Or you could say that 3 moles of A react, and that will form 4 moles of D. So there's going to be a ratio of 3 moles of A reacting for every 4 moles of D that form. Or you could do it for the other reactant. 2 moles of B react to form 4 moles of D. And you can write these ratios in either order. Either 3 on the top, 2 on the bottom, or you can flip the ratios, whatever you need to be able to convert amounts of one substance into amounts of another. So all of these ratios that you can get from the coefficients, which in this case there's even more than I've written here, these are all going to be unit factors, conversion factors that allow us to convert between one amount of substance and another. All right, and so that allows us then to do that, recognizing that the coefficients give us mole ratios. So what I'm going to write out here, and then maybe have time for one quick example, is sort of the process of stoichiometry in a very sort of diagrammatic and general form. So there's going to be a lot of ways that we do stoichiometry problems. The one that we're primarily going to start with is called a mass-to-mass stoichiometry. That's the most convenient way to do it in a real chemistry setting as well. I have this mass of one substance that I measured out. How much mass of the other substance do I need to react with that? Or how much mass of the product will form from that? That's called a mass-to-mass stoichiometry. We're converting mass of one substance into mass of another. So that's what we're trying to do. We have mass of one substance, which we'll call A, that's involved in the equation. And we want to find the mass of another substance, B, a different substance, that's involved in that same reaction. where A and B are either two different reactants or two different products, or one reactant, one product, just two different substances that are on either side of that chemical equation, and we're trying to convert how we do this. Now the reality is we don't have a direct way to do this because a balanced chemical equation doesn't tell us the relative number of grams of each substance that reacts. It always just tells us the relative number of moles of each. So the way we're going to do this is sort of in a multi-step process. If we have the mass of A and its molar mass, we can convert into moles. So using the molar mass or molecular weight of substance A, we can convert into moles of that substance. And then the key step in any stoichiometry problem is once we have moles of one substance, we can use the reaction coefficients to convert into moles of any other substance. So we're going to use the reaction coefficients here, or the stoichiometric coefficients as they're often called. And that's going to allow us to figure out how many moles of B would then be involved in this reaction. And then often we still want to get back to the mass of substance B, not stopping at moles, and so then we're going to use its molar mass to go back into this. And we can really do this in a lot of different orders, a lot of different sequences, depending on what we're given and what we're asking. But this is going to be the series of steps that covers the vast majority of these mass-to-mass stoichiometry problems, using molar masses to convert between mass and moles, and then using reaction coefficients from the balanced equation to convert moles of one substance into moles of another. Now the other little variation on this, I should have drawn extra boxes, but I didn't, but sometimes what we'll also ask you to do is figure out how many atoms or molecules of one of the substances involved. Again, not very practical from a chemistry lab standpoint, but something that we can calculate where you're going to use Avogadro's number to do that. So whenever you're doing stoichiometry problems, which we're going to get more and more varieties of them as we go through these next couple chapters, you always have to remember all of your relationships involving moles, because you have to get to moles to be able to do stoichiometry, but then you can also convert into other other quantities as well using the different relationships. So Avogadro's number would allow us to also calculate how many atoms or molecules of each substance is involved as well. All right, I think my pen died, so that's telling me there's time to stop. I'm not going to reset my tablet for you guys. All right, that's great. So let me check real quick, make sure it's not the pen, and that's actually like the tablet that's flaking out. Sorry. Yeah, we're done. Okay, so I'll finish writing this out in the notes, and then we'll go through example problems next time to see how this works. We're about at the end anyway, so I'll see you guys next time.